Hi folks, today we're going to have a look at the 2019 National 5 Physics paper, section 1, which is the multiple choice questions. And question number 1 is a question about vectors and scalars. So let's remember that vectors are quantities which have both magnitude and direction, and scalars have only magnitude. And these are some of the ones that we should know about at National 5 Physics level. So scalars include distance, speed, mass, time, and energy, whereas vectors include displacement, velocity, force, and acceleration. And we need to also realize that weight is the force due to gravity, so weight is a force. So answer A are technically both vectors because weight is a force and acceleration as well are both vectors. In the others, kinetic energy is a scalar in answer B. In C, mass is a scalar. In D, speed is a scalar. And in E, speed again is a scalar. So the correct answer is A. Question number 2. A car is travelling at 6 meters per second along a straight level road. The car then accelerates uniformly at 2 meters per second for 4 seconds. The final speed of the car is... So we're going to use our A equals V minus U divided by T equation here. And we're going to insert the relevant numbers into there. The acceleration we're given is 2. U is the initial speed, so the speed that the car is traveling at originally, 6 meters per second, and T is the time, which is 4 seconds. Do a little bit of rearranging. So I multiply the 4 to the other side and get 2 times 4 equals V minus 6. And if we're subtracting 6 on the left-hand side, to get rid of that from the left-hand side, we need to add 6 to the right-hand side. And that gives us a value of 14 meters per second, which is answer B. Question number 3. The graph shows how the speed V of a car varies with time t. During which part of the journey does the car have the greatest acceleration? Well, this is a velocity time graph, and the acceleration is how quickly the velocity changes over time. So the rate of change of velocity. And that is given by the gradient of the velocity time graph. So the place on the graph with the steepest gradient will have the greatest acceleration. And that is S to T, which is answer E. Number 4. A ball is kicked horizontally off a high river bank as shown. The ball lands on the lower side of the bank at X 2 seconds after the ball is kicked. The river is 3 meters wide. The effective air resistance on the ball is negligible. The distance D between the edge of the lower bank and X is... So, what we need to understand, first of all, is that the horizontal velocity of the ball is constant because, as it says in the question, the air resistance is negligible. So the ball kicked at 8 meters per second will continue horizontally at 8 meters per second all the way until it hits the ground. Its vertical velocity will increase, but we don't need to worry about that here. So we can find the total distance travelled by the ball. Distance equals speed times time, which is 8 meters per second multiplied by 2 seconds, which is 16 meters. That tells us this distance here from the bottom of the cliff to point X is 16 meters. However, the river is 3 meters wide. So to find the distance D on that diagram, we need to subtract 3 meters from the 16 meters, which gives us 13 meters for D. Answer C. Number 5. The table gives the distance from Earth and approximate surface temperature and age of 5 stars. The student makes the following statements based on this information. Firstly, the distance from Earth increases, the age of the star decreases. Well, that's not correct. If we have a look at the data here, the distance from Earth increasing does not seem to have any relationship at all on the age of the star. 2. As the age of the star increases, the approximate surface temperature increases. Again, this is not true. If we look at the youngest star, which is Betelgeuse, 7.9 times 10 to the power 6, it has the lowest surface temperature. But the next youngest star is Rigel, which has the greatest surface temperature. So there's no real relationship. And the third statement is there is no apparent relationship between the distance from Earth and the approximate surface temperature of the star. That is true. If we look at that data, there doesn't seem to be any obvious relationship. So statement 3 is correct, which is answer C. Number 6. A geostationary satellite orbits the Earth. Which row in the table shows the altitude above the surface of the Earth and orbital period of the geostationary satellite? So a geostationary satellite is geostationary because it orbits the Earth in a time of 24 hours, which is exactly the same length of time as it takes the Earth to complete one revolution, which is why it appears to stay above the same point on the Earth all of the time. So the period of orbit is 24 hours. The distance above the Earth's surface is just one of these things that we have to learn, and it is 36,000 kilometers. Answer B is the correct answer here. Number 7. The weight of a robot on Earth is 240 newtons. The weight of a robot on Mars is... So, weight equals mass times gravitational field strength. And the gravitational field strengths of Earth and Mars are given in the datasheet at the front of the exam paper. And we can see here that the gravitational field strength of Earth is 9.8 newtons per kilogram, and on Mars it's 3.7 newtons per kilogram. So I know the weight on Earth. In order to find the weight on Mars, I need to multiply its mass by the gravitational field strength on Mars. We don't know its mass, so we have to first use its weight on Earth to find its mass, and then use that mass to find the weight on Mars. So, firstly, using the weight on Earth to find Mars, we use W equals m times g. Its weight on Earth is 240, g on Earth is 9.8, so the mass is going to be 240 divided by 9.8, which is 24.5 kilograms. Mass does not change anywhere in the universe, and therefore that mass on Earth, 24.5 kilograms, is the same as the mass on Mars. So we can do the same calculation, W equals m times g, for Mars. We're taking that mass and multiplying it by the gravitational field strength on Mars, 3.7, and we get a value of 91 newtons, which is answer C. Number 8. A hairdryer is connected to a 230 volt supply. The current in the hairdryer is 2 amps. The electrical charge that passes through the hairdryer in 5 minutes is... So, nice, simple, quick formula question here. Q equals I times T, charge is current times time, which is 2 amps multiplied by 5 minutes converted to seconds, which is why I've written 5 times 60 here, which is 300 seconds. So 2 times 300 seconds is 600 coulombs. Answer C. Number 9. The graph shows how the resistance R of a thermistor varies with temperature T. The thermistor is connected in a circuit. At a temperature of 50 degrees Celsius, the current in the thermistor is 0.004 amps. At this temperature, the voltage across the thermistor is... So, we know voltage, as we know current rather, and we can work out the resistance from the graph, so we're going to use V equals I times R to find the voltage. The current is 0.004 amps. The resistance, we need to look at our graph and find out what resistance the thermistor has at 50 degrees Celsius, and we find that it is 2 kilo ohms. So 0.004 times 2 times 10 to the power 3, which gives us 8 volts, which is answer D. Question 10. A student sets up the circuit shown. In which circuit will both LEDs be lit? So for an LED to work, it has to be what's called forward biased. And in terms of these diagrams, that needs to look like the pointy end of the LED has to be pointing towards the negative side of the battery. So in A, that LED is pointing towards the negative side of the battery, but that one is not. In B, that one is pointing towards the negative side of the battery, but that one is not. In C, that one is not pointing towards the negative side of the battery, although that one is. In D, neither are pointing towards the negative side of the battery. And finally, in E, both LEDs are pointing towards the negative terminal of the battery. So answer E is the correct one. Number 11. A circuit is set up as shown. The room temperature is 20 degrees Celsius. The lamp is off. The lamp will light when? So the room temperature being 20 degrees Celsius is a bit of a red herring in this question. It's totally irrelevant because in this circuit we have a light-dependent resistor, not a temperature-dependent resistor. So what's going to make the transistor turn on? Well, the transistor is going to turn on when its base emitter voltage, which in this case is the voltage across the light-dependent resistor, rises above the switching voltage of the transistor, which is about 0.7 volts. So the transistor will switch on when the voltage across the LDR rises above 0.7 volts. Now, what's going to make the voltage across the LDR rise? Well, it's going to gain a greater share of the supply voltage if its resistance increased. So the voltage across the LDR will rise when the resistance of the LDR rises. What's going to make the resistance of the LDR rise? Well, the resistance of the LDR will increase if the light level decreases. So decreasing the light level below a certain value will cause the transistor to turn on. So answer A. Number 12. A circuit is set up as shown. The student makes the following statements about the readings on the voltmeter. V1 equals V2. So if we look at these resistors, V1 and V2, V1 is the single resistor on its own. V2 is connected across one of the resistors connected in parallel. So will these two voltages be equal? Well, it's possible they could be equal. V1 plus V2 will have to equal the supply voltage, but they will not necessarily be of equal size. So that is not true. V2 equals V3. So these are two voltages connected across two resistors in parallel. In a parallel circuit, the voltage across each branch of a parallel circuit is the same. So that is true. And Vs equals V1 plus V2. Well, yes, that is true as well, because in a series circuit like this, the supply voltage will be split between the components in the circuit. The two resistors in parallel are effectively one part of this series circuit. They act together as one individual resistance in series. So the V1 and V2 added together will give the supply voltage. So 2 and 3 are both correct. So answer D. Number 13. A solid substance is placed in an insulated container and heated. The graph shows how the temperature T of the substance varies with time. To calculate the specific latent heat of fusion of the substance, a student would use the time from section. So what's going on here? Well, it starts off at P as a solid and heats up to Q. and then it will melt and become a liquid. And then it will heat up as a liquid from R to S, and then it will boil and become a gas. So Q to R shows the substance melting from solid to liquid, and S to T shows it boiling from liquid to gas. So latent heat of fusion. Fusion has to do with the change of state between solid and liquid, the melting state. And that, as we can see from our diagram, is Q to R, which is answer B. Number 14. The pressure P due to the liquid at a depth of H is given by the relationship P equals rho GH. Slightly confusing because we've got two symbols that look very, very similar. We have a P and we have the Greek letter rho, which is the curly P in the formula next to the G. Anyway, the curly P, rho, it's a Greek letter, is the density of the liquid, and G is the gravitational field strength. A liquid has a density of 990 kilograms per cubic meter. When the pressure due to the liquid is 1,470 pascals, the depth of the liquid is... So, this looks like a confusing and complicated question. Actually, it's not. We just need to insert the right numbers into the right place in our formula. So, we're given the pressure, 1,470. We're given the density, 990. G is the gravitational field strength, which we have from the data sheet, is 9.8 newtons per kilogram. And H, the depth, is what we're trying to find out. So we can rearrange that formula to find the depth, and we get 0.15 meters, which is answer B. Question 15. A car is parked in the sun for some time. During this time, the air pressure inside the tyre increases. The reason for this increase in pressure is, well, what's going to happen if the car is parked in the sun is that the air inside the tyre will heat up. When a gas heats up, the particles will move faster. They will gain kinetic energy, and therefore they will hit the inside of the tyre harder and more often, and that will cause a greater force on the inside of the tyre, which will cause a greater pressure. So the answer to this question is E. The air particles in the tyre are moving with greater kinetic energy. Number 16. The temperature of a sample of gas in a container is 20 degrees Celsius. The volume of the gas is 0.3 cubic meters. The container is free to expand in order to maintain a constant pressure. The temperature of the gas is increased to 50 degrees Celsius. The volume now occupied by the gas is... So, what we need to notice is that the two temperatures that were given are in degrees Celsius. When dealing with this sort of question, a gas laws question, we always have to be working in Kelvin. So we're going to convert our 20 degrees Celsius by adding 273 to give it 293 Kelvin. And we're going to convert our 50 degrees Celsius into Kelvin by adding 273, which gives us 323 Kelvin. And then we're going to use the formula V1 over T1 equals V2 over T2. 0.3 over 293 equals V2 over 323. Rearrange the formula a little bit, and we get this value of 0.33 cubic meters, which is answer D. So increasing the temperature by 30 degrees does not actually increase the volume of the container by a large amount. Number 17. The following diagram gives information about a wave. Which row in the table shows the amplitude and wavelength of the wave? So, in this sort of question, I would urge you to do a little bit of drawing on your paper. The amplitude, as shown in green on this diagram, is the distance from the midpoint or from the equilibrium position up to the maximum or minimum, the crest or the trough of the wave. So that's going to be half of 6 meters, which is 3 meters. So the amplitude is 3 meters. The wavelength is one complete wave's worth. And if we look at the blue writing on the diagram, we can see that the wave that is drawn here for us is made up of 3 individual wavelengths, 3 complete wavelengths. So 3 complete wavelengths make 24 meters. So one wavelength is going to be 24 meters divided by 3, which is 8 meters. And that is answer B. Number 18. A student is studying waves with a period of 80 milliseconds and a wavelength of 4 meters. The frequency of these waves is... Okay, so the wavelength is extra information here just to throw us off the scent. The way to work this out is using the formula frequency is 1 over period. 1 over 80 milliseconds, which is 80 times 10 to the power of minus 3, which is 12.5 hertz. Answer C. Number 19. Which of the following diagrams shows the diffraction of water waves as they pass between 2 walls? Okay, so the answer is D. The reason it is not any of the others, it is not A, because A does not show diffraction happening. It just shows the wave being blocked by the walls. B sort of shows diffraction happening, but it doesn't show the waves spreading out as they go past the wall. It also does not show a flat section along the wave front. If the gap between the walls is of a larger size than the wavelength of the wave, then we would see a flat section in the middle and then just curved bits at either side, whereas the waves that are passing through the gap in B shows only curved waves, so it would not be B. C and E both show the wavelength of the waves changing after they have gone through the gap. That does not happen. The wavelength of the waves as they diffract through the gap is unchanged. So C shows the wavelength decreasing and E shows the wavelength increasing. Neither are true. The wavelength would stay the same. So the only one that is correct is answer D. Number 20. A ray of red light passes through a glass block as shown. Which row in the table shows the angle of incidence and the corresponding angle of refraction at point X? Well, we can see the light is coming, as we look at it, down through the block of glass. So the angle of incidence is always the first angle that we come to, as indicated by the arrows on the ray diagram. So the angle of incidence and the angle of refraction are both always measured from the normal. So the angle of incidence is that angle there indicated in red. And we're given the angle between the light ray and the block of glass. So the angle between the normal and the light ray will be 90 degrees minus the angle we're given, which is 35 degrees. And similarly for the refracted ray, the angle of refraction will be 90 degrees minus the 30 degrees shown in the diagram. So angle of incidence 35, angle of refraction 60. Answer A. Question 21. Which row in the table shows the paths taken by an alpha particle and gamma radiation as they pass through a uniform electric field between 2 metal plates? Okay, so an alpha particle is made up of a helium nucleus, 2 protons and 2 neutrons. That means the alpha particle has a positive charge. So when an alpha particle passes through this gap, being as it has a positive charge, it will be repelled away from the positive side of the electric field and attracted towards the negative side of the electric field. So in the diagram that we're looking at, the alpha particle would be deflected downwards. The gamma ray does not have any charge. It's not a particle. It's just a wave. So it does not have any charge and therefore is unaffected by the electric field. So we're looking for the option where the alpha particle is deflected downwards and the gamma ray carries on unaffected through the gap. And the one that shows that is answer B. Number 22. For a particular radioactive source, 1,800 atoms decay in a time of 3 minutes. The activity of the source is, so A equals N divided by T. Activity is the number of radioactive decays divided by time, which is 1,800 decays divided by 3 minutes converted into seconds. So 3 times 60 is 180 seconds. So 1,800 divided by 180 gives us 10 becquerels. Answer A. Question 23. The crew on an aircraft during a transatlantic flight are exposed to cosmic radiation at an equivalent dose rate of 5 microsieverts per hour. The crew completes 6 transatlantic flights each month. The average duration of a flight is 8 hours. The equivalent dose received by the crew due to cosmic radiation during transatlantic flights in 1 year is, well, if we work out the equivalent dose per year, the equivalent dose per flight, we have the equivalent dose rate equals equivalent dose over time, which is equivalent dose rate is 5 microsieverts per hour. The time of one flight is 8 hours. So the equivalent dose is going to be 5 microsieverts per hour times 8 hours, which is 40 microsieverts for one flight. How many flights do they complete in a year? Well, it says that they do 6 transatlantic flights each month. So 12 months in a year, there will be 6 times 12 flights in a year, which is 72 flights per year. So if we know each flight accumulates 40 microsieverts of equivalent dose, and there are 72 of these flights per year, then the equivalent dose for the year will be 40 microsieverts multiplied by 72 flights, which is 2,880 microsieverts, which is answer E. Number 24. A radioactive tracer is injected into a patient to enable doctors to check the function of a patient's kidneys. Radiation from the tracer is monitored outside the patient's body by a detector. Which row in the table shows the most suitable type of radiation emitted and the half-life for the tracer? So, first of all, the type of radiation emitted. It's most likely they would use gamma radiation for 2 reasons. Gamma radiation is the most penetrating, so therefore will be easiest to detect outside of the patient's body. Gamma is also the least ionizing, so is therefore the least likely to cause harm to the patient's body tissue. The half-life of the tracer we want to be short because we want the radiation to be hazardous to the patient for as little time as possible. So we would rather use a half-life of 6 hours rather than 6 years. So the answer is gamma and 6 hours, which is answer D. And the final question, question 25, the activity of a radioactive source is 56 megabecquerels. The activity of the source 40 hours later is 3.5 megabecquerels. The half-life of the source is, so what's going on? Well, half-life means the activity will fall by half in that period of time. So the activity falls from 56 to 28 in one half-life. Another half-life, a second half-life, will see it fall from 28 to 14 megabecquerels. A third half-life will see it fall from 14 to 7 megabecquerels. And a fourth half-life will see it fall from 7 to 3.5 megabecquerels. So 4 half-lives occur in this 40-hour period. Therefore, one half-life is 1/4 of that 40-hour period, which is 10 hours. Answer B. And that completes the question paper. I hope this was useful to you and you get something helpful out of it. I will talk to you again another time.